My name is Taylor Kramer, and my thesis presentation is on swarm robotics. I'm focusing on this emerging technology as I have a personal background in the robotics field and find it super interesting, particularly given its bio-inspired nature. The basic idea of swarm robotics is that rather than one super complex big robot, you put together 100 small and simple robots that can work together to accomplish a task. These swarms can be made up of aerial vehicles, ground vehicles, or a combination of the two. This is useful in a variety of applications, from search and rescue to disaster relief and self-driving cars. Throughout the semester, I have transitioned my work a bit from the prospectus version to what I want to accomplish in my final thesis. I think last semester I focused a lot on specific error detection algorithms and normalized deviance, but after looking at a lot of feedback and considering what parts of it I'm really interested in, I decided to take a more global view of swarm robotics and swarm intelligence as a whole. For my thesis going forward, I am focusing on the analogy to nature, since swarm intelligence is a very nature-inspired development, trading zones, and anticipatory governance looking forward. I believe that this will allow me to present a more cohesive view of swarm robotics and allow me to cover a better range of the complexities within it. Usually, when you think of robots, nature is the furthest thing from your mind. In a lot of applications, however, thinking in terms of nature is super useful. A commonly recognized use of bio-inspired design in robotics is its use in locomotion. A good example of this is the majority of Boston Dynamics' popular robots, such as Atlas and Spot, shown here in the middle of the page. These robots walk in a very humanoid or dog-like way, allowing them to deal with the changing landscape. These are preferable in certain types of situations where you need a more flexible range of motion for odd terrain, which typical wheels or rotorcraft cannot handle. For a full application of robotics, you don't want to be limited to a smooth and flat factory floor. As you can see here, there's a wide range of ways this locomotion is accomplished, and they take inspiration from a variety of creatures. For example, the mechanism on the left has a specialized surface adhered to the ground contacting areas of the device, which mimic the unique grippiness of gecko feet. I already mentioned the robots in the center, and then on the right, you see a few military robots. The small one on the top is called a sand flea and can jump 30 feet into the air using a piston. The bigger one on the bottom has curved paddles as feet, which can be easily used for motion on land or in water, too. The next continuation of bio-inspired design is the application into swarm intelligence. It was inspired by the behavior of insects, such as ants and bees, and prioritizes quantity over complexity, allowing large numbers of simple robots to complete a difficult task. This is a large multi-robot system without a centralized control. Sensing is distributed across all of the robots, and they all act in a more localized manner, communicating necessary information to nearest neighbors, which reduces the need for a global map and allows for more dynamic planning and navigation. A large perk of this is that not every robot has to be perfect. For example, if one robot fails for one reason or another, you still have 99 completing the task and coordinating with their constantly rotating neighbors. This makes swarms a bit more fault-tolerant than one large robot, but it depends on the type of error, and these error detection algorithms are still kind of in development. I think the most interesting part for me, and what distinguishes swarm robotics as a special class of multi-robot systems, is the concept of decentralized control and communication. Rather than one central controller bot giving out global instructions, each robot in the swarm acts according to its own local environment. This improves the resiliency of the swarm because each robot contributes equally and also relies on other members of the swarm in a balanced way. Here I have an overview of the STS frameworks I'm using and the key areas they apply to or are relevant towards. Swarm robotics relies heavily on trading zones as it is an interdisciplinary field. This means that all throughout the process of working on swarms, a team would usually be made up of experts in engineering, biology, social scientists, and stakeholders. Teams more focused on implementation rather than research might use a more engineering-skewed team, relying on and basing models off of prior work from biologists and social scientists that have been published in journals. Since this field hasn't been around for very long, I think the continuation of trading zones is super important to keep up with new behaviors observed and to continue learning from nature. Users and stakeholders also need to be included in the trading zone to provide their knowledge of needs which the engineers may not be able to meet separately. This allows them to work together towards a solution that fits the unique needs of the swarm application. Oftentimes, the military is actually a very important stakeholder since this is an emerging technology and robots are often used in risky areas that can be dangerous for humans to traverse. This relationship will influence the types of swarm behaviors that are developed first. Many of us have seen videos of drone swarms playing at a light show in the sky, but the more advanced versions of this technology are supported and developed for life and death scenarios. As a result, the biggest support goes to search and rescue type operations. The question I try to address here is how do we guide the transition from swarms interacting in that type of an environment to existing in a more casual and populated environment that we can maybe see in our day-to-day lives. As a framework, I'm also using an analogy to nature to bring together trading zones and anticipatory governance. The whole idea here is that if a problem has been solved in nature already, why not try to bring that solution into our work here too? I believe that this is a very useful tool with swarms given that many of the behaviors are already based on nature as well. Similar to how biomimicry and movement provided a nature-based way of moving in the natural environments that we struggled with, I think continuing to look towards nature for solutions could prove to be key. Here in the slides, I show how insect experts made models to represent the communication structures they observed, and ran simulations based on the models to learn more about ants and wasps. One example simulation they ran focused on observing building patterns in wasps, and how they left clues in their environment so that the next wasp could just fly up and continue the previous wasp's work. Engineers then borrowed these algorithms and mathematical patterns to apply towards multi-robot interactions and ran experiments with those models to learn more about how robots would interact with each other. I included a bit of that information because I think finding solutions in nature would follow a very similar path to the discovery method that led to swarm robotics in the first place. Finally, I think it's time to talk about anticipatory governance. This framework is particularly useful looking forward for when swarm robotics becomes more of a thing outside research applications. As such, now is the best time to be thinking about things like this. One of the big concerns, as there always is surrounding human-robot interaction or coexistence, is the topic of ethics. This is an ongoing discussion with most forms of human-robot interaction, so I'll base a majority of my analysis on that, with special care taken to acknowledge the swarm factor as well. In a similar boat is the anticipatory governance surrounding machine learning and AI cheating, since fully autonomous systems are more difficult to do testing on. Already, there are some rules and regulations that limit the application scope for swarms in current usage. For example, Pentagon doctrine states that lethal force, aka a weaponized system, requires a human-in-the-loop segment. As such, a fully autonomous system like swarms would not be weaponized for any military purpose. The two sections most of interest to me when it comes to anticipatory governance, however, is the security of devices and the propagation of error if one or more robots becomes compromised. From the tech side, there are a variety of error detection algorithms that make them more fault-tolerant systems, such as something called collective self-detection, or CODE for short. This is a method found in natural group dynamics, where a sick ant will identify itself as being sick compared to its healthy neighbors, and then self-isolate to go off and be sick on its own so that it won't negatively affect its neighbors, kind of like its self-quarantine. On the policy side, however, there is much work to be done still to ensure fail-safes and other things so that outside players cannot quietly break into the autonomous systems without anyone knowing. So, there's a summary of my thesis. If you have any questions or comments or things to add, let me know in the forum.